All right. You want to kind of call them off? I don't have the list of who's there.
Sure. We have Chris is here, Joel, John Hawk, Roger, and Tungsten. And I apologize if I'm pronouncing that wrong. How many of you can talk to us? I know Chris can't. Joel can very nicely. John, I don't. Maybe John can't. Roger, do you have a mic hooked up?
Rich, hang up on that.
Okay, for everybody who can't talk to me, if you could, just so that we know that you can hear us, if you could raise your hand by clicking on the little hand next to your name. Thank you.
Can you guys hear this?
Yes, we can hear that.
As loud as it goes.
Good. John, can you hear me?
I'm having trouble.
Oh. Okay. It looks like everybody can hear us, Don, so I think we can get started.
All right, very good. Well, welcome to another Brown Bag session. If you can't catch all of this or you want to review it later on, Wendy will be recording it. And the title of this one is Selecting Datum Features. It's all about what you do not find in the standard. I'd like to point out that the standard doesn't have a lot of application. We did add a little bit this time. But I guess another way to say, since you're not finding it in the standard, this is my opinion. So we may have some nice discussion at the end of what I present. And that would be great. In our training, we really emphasize that GD&T can be as easy as 1, 2, 3. One is to establish datums for dimensional origins on your parts, or look around the drawing to find those datum features that establish the datums. And 2, a lot of people forget to do this, but that's to put controls on the datum features, because they are features. People think, oh, it's a datum, it's perfect. No, the datum isn't on the part. So we need to control those. And the 2009 revision of the standard points that out very clearly. And then you locate everybody else. Everybody has to be somewhere on the part. When people say, I don't care where it is, I tell them get rid of it. You know, every feature costs money. So if you don't care about a feature, just get rid of it. Then they want it. They say, oh, I need to look through there or something, so we have to locate those. And then I'm getting a lot of background noise. I don't know where that's coming from. And then step 4, only if necessary, is refined with additional datum reference frames and geometric controls, but only if necessary. So I want to go back up here to where we're establishing datums. Just how do we go about that? Well, if we look to the standard for guidance, we're told that the datum features are selected based on their functional relationship to the toleranced feature and the requirements of the design. Okay, that's kind of a nebulous thing in some sense.
Don?
Yeah.
Joel has a question for you.
Already? Okay.
I think we resolved it. I was not seeing the webinar on the screen, and now I am.
Okay.
Excellent.
Okay, so we're all set?
Thank you.
Okay. And then the one that a lot of people hang their hat on is this bullet from the standard. It says to ensure proper assembly, corresponding interfacing features of mating parts should be selected as datum features. And this is one that I have some trouble with. When we were working on the 2009 revision, I pointed out that I think this can mislead people. And I'm going to show you how and what I might want to replace this with as we go through it. The datum features should be accessible on a part. I've got to be able to get to them because I'm going to use them to set the part up for inspection. And I always think back to a weldment that someone brought me. They had a drawing of a weldment. It was a tube. They had welded plates on both ends, and they called out the inside diameter of the tube as their primary datum feature. With those plates on the ends, there was no way to get to the datum feature. So they have to be accessible. They have to be a sufficient size to permit their use. And the use of a datum feature is to constrain some degrees of freedom that the part has in space. Small or short features do not do that very well as a primary datum feature. They might work okay as a secondary or tertiary datum feature, but I'll look at a sheet metal drawing and somebody will call out a hole going through the sheet metal as a primary datum feature, which means it has to reproducibly constrain 4 degrees of freedom. It's a cylindrical feature. Cylindrical features as primary datum features constrain 4 degrees of freedom. That hole in the sheet metal isn't long enough to do the job. So that's one that I find a lot of people messing up on. And then datum features must be readily discernible on the part. When you're dealing with symmetrical parts, which are nice, we like symmetrical parts, especially for designed for assembly purposes or poka yoke error avoidance. The more symmetrical the part, the easier it is to put together. But if you're just using one side of a symmetrical part, for instance, and people could flip it over, then which one do you use? It can be very confusing on the drawing. The figure that was added is shown here in the 2009 revision of the standard, and this was to show you that you look at the function of the parts and you select the interfacing mating surfaces. So let's take a look at those features. Let's see, I have this plane on the crankshaft, and then on the adapter I have a plane coming up against it, so that's an interfacing mating surface. And then we have the pilot diameter going down into this bore in the crankshaft. Let's look at some other interfacing mating surfaces. Up here at this end of the adapter, this shown in blue is definitely an interfacing mating surface. It mates with this bore in the pulley. Another one is the shoulder. It's going to mate with that surface on the pulley. And here on the washer even, I have a couple of interfacing mating surfaces, one on the pulley and one on the washer. So the question is, okay, I'm supposed to use interfacing mating surfaces as datum features. Does that mean all of these features I'm showing you should be datum features? And the answer is probably not. But what do the red features have in common? As we look at this feature, and especially on the adapter, this feature, these red features are taking away some of the part's degrees of freedom in space. In another webinar or another brown bag, we talked about how all parts in space have 6 degrees of freedom. And if I am going to make full contact on this face, that's going to take away 3 of the degrees of freedom, 1 translation and 2 rotations. And then this pilot diameter is going to constrain 2 degrees of freedom, 2 translations. The only thing the adapter will be allowed to do is spin. And once we put the screws in there, that'll stop the spinning. But I don't need to use the holes for the screws as datum features because there isn't anything else to align to those. So on this adapter, we'll see that the face and the pilot diameter have been called out as datum features. On the pulley, the same thing. This is a feature that is constraining 4 degrees of freedom on the pulley. And then this face is constraining 1 translational degree of freedom when it comes up against that shoulder. And I won't bother talking about the washer here. Let's just look at these parts. So as I look at the drawing here for this adapter, they've made this face primary, takes away the 3 degrees of freedom. They made the pilot diameter secondary, but they didn't make these interfacing mating features datum features. They just toleranced them. Okay, we're locating this shoulder with profile, and we're locating this diameter with a position tolerance. So they're toleranced back to A and B, but they didn't make them datum features. And that's why I was showing them in blue in the assembly. And with the pulley also, the bore is made the primary datum feature, constrains 4 degrees of freedom. This shoulder is going to take away 1 degree of freedom, so they called that the secondary datum feature, B in this case. So those are my interfacing mating surfaces. But I had another interfacing mating surface up here that isn't a datum feature. Sorry, I jumped a little fast there. So here's one more selection criteria that is not found in the standard, but it's the one that I live by most of the time. And that is select the features that in the parts function constrain the most degrees of freedom. Now, why do I want to use that as a criterion? Well, usually we're worried about variation in our assembly. When we put all the parts together, we worry about how much variation there is. If you follow this approach right here, it will reduce the variation in your assembly, and I'm going to illustrate that here in just a few minutes. If we let production or inspection select the datum features, you know, that's usually how it goes. If you have a drawing review, you get the folks together, and production wants certain datum features because that's how they hold it in production. And inspection says, no, I want to hold it like this to inspect it. And of course, design is there saying, well, those aren't functional many times. So production is going to pick their datum features based on the process or ease of setup for inspection. The question I often ask then is, if we do that, if we put those, pick those as datum features on the drawing, and you change the process, you go to a different supplier and they hold the part differently, are you then going to go back and change the drawing? And the answer always comes out, well, no, we're not going to go back and change the drawing. And the reason is, look, the function of the part remained the same. So that's a question that often helps to kind of get us off this using those processing datums rather than functional datums. And for auxiliary datum reference frames, and what I mean by that is once you have your initial datum reference frame, you locate some other features to it, and then you might want to make those features datum features. If we think about something like the turret, which is a big casting on the M1 tank, I was told that there's 72 datum reference frameworks on that turret. Every time they're mounting some little sensor or whatever, they set up a new datum reference framework. So I'd call those the auxiliary datum reference frames. Well, for those, I'd ask the question, whoops, did I go by it there? Maybe my question was there. Yeah, select the features that, in the parts function, constrain the most degrees of freedom of mating parts. In other words, are these features on the part that are going to mate with others, and they're actually going to be constraining, taking away the degrees of freedom of that mating part. On this part, these blue features could have been picked as datum features. I know a lot of people that would do that. They might make this diameter, let's say C, and they might make this shoulder D. And they might then put a perpendicularity on this shoulder with respect to C. Or they may not have called this out as D. They might just call this C and then say perpendicular to D. I probably wouldn't bother with that because when I put the mating part on here, it's going to hit the high point whether this shoulder is real perpendicular or not. So we chose not to, in the standard, call these out as datum features. Later on, I'll show you a part where I have added auxiliary datum reference frame. So here's the criteria for selecting an auxiliary datum reference frame, but you might also consider using composite tolerancing or simultaneous requirements. You know, these are two ways to create patterns that tie a bunch of features together. And so you can say, well, I'm going to locate these from my datum reference framework, but then I'm going to tie them together with a composite tolerance or because of simultaneous requirements, which we covered in a previous brown bag. Keep in mind, when you keep adding datum features, there's always setup error. I set the part up to measure it, I take it away, I bring it back, it won't end up exactly where I put it. You know, there's always those little bits of setup error that can throw things off, give you different results. So why select datum features based on their constraining degrees of freedoms in the assembly? Once again, because we want to reduce the variation that ends up in your final assembly. In general, that's not always true, but in nearly all assemblies it is true. If you take this approach that I'm pushing here in this brown bag, your overall variation in the assembly will be reduced. If you pick other features as datum features, you'll have to tighten the tolerances on the part in order to get the same amount of variation. I'd like to illustrate that. Let's take this little assembly that we use in our applications and tolerance stack-up course. And let's say that I'm worried about the minimum distance here. I want to know what that minimum distance will be from this plate up to the top of the roller. Now, to get to the roller, I have to go through this casting here, the machine casting, we're calling it the frame, and then I have to go through this bracket, and then I have to go through the stud to figure out where this roller will end up. So I might start with the roller and using our criteria. Who would I choose as my primary datum feature? And since a lot of you don't have microphones, I guess I'll go ahead and answer it. As I look at the assembly and ask what feature on this roller is going to end up doing the constraining of the degrees of freedom, and I'd say it's that inside diameter. So I'd be very tempted to make that my primary datum feature. And I'm worried about the surface of the roller, certainly, and I'll have something like a run out going back to that axis established by datum feature A. You talk to the supplier, and the supplier often will want to turn this around. He'll say, don't you know anything about making parts? I want to grab this on the outside diameter, and then I'm going to machine that hole in there, that bore. So I started with this drawing, and let's see what this means. Well, first we fill A, regardless of its material boundary, so maybe with the biggest pin that'll fit in here. And then to check the run out, I'm going to check slices all the way along here. Right, I'll be looking at different slices because it's circular run out, and the slices will be the circular slices. I don't want to mislead you by showing this going back and forth like that. So I'll check this slice, I'll rotate the part, then I'll go to another slice. So I'm looking at the variation in the surface of the roller. That'll help me understand what will happen in the assembly. But let's say that we switch these around. We make the outside diameter the datum feature, and then we put the run out on that hole because that's what the supplier would like to see. Well, I close in then on that outside diameter, and you notice I'm only hitting the high points. I ignore the low points that the indicator picked up that my design is probably interested in. And then I'm going to come in with an indicator and do the run out check, which is going to look at the highs and lows in here when I'm really concerned about how the highs are contacting that stud, that mating part. The lows aren't as critical. So this one over here on the left is representing design intent, and I'm just going to say no to this one, which is more metrology based or production based. The line I usually use is, the supplier will say, well, I want to grab it on the outside diameter, and I'll say, yeah, and I want a pony for Christmas. We don't always get what we want. That doesn't go over real big, by the way. Okay, let's go back to this assembly then. Now I look at the stud. And people will say, well, you see this journal bearing right here that roller rides on? That's a critical feature. It's an interfacing mating surface. Shouldn't that be a datum feature? Not in my book. I ask what locates and orients the stud in its assembly. The stud gets riveted onto this bracket. So when I rivet it down, it draws it up against this surface right here, and it centers up on this 11.5 diameter. So the most degrees of freedom will be constrained by that surface. So I'll make that my primary datum feature. I'll make this diameter my secondary datum feature. And yeah, this is an important diameter. I'm going to have a good control on it and a tight size tolerance because there's a good fit to the roller. But I'm not going to make this a datum feature. Now, if the design changed, let's say I had a casting coming up here and got rid of these two parts and just had a casting, and I was going to press this pin down into a hole in the casting. So I had this nice machined hole, and I was doing a light press of the stud in there, so I'd make this longer. Then things would switch around, wouldn't they? This diameter would become my primary datum feature, and then I would only hit one high point on the shoulder when I pressed it into place. Now, what I really wanted to get to is this bracket. As we look at the bracket, it mounts up against this surface. I put these two screws in there. This screw is a nice fit on that hole. And once I have it up against that surface and that first screw in, the only thing this can do is rotate. So I have the slot, very robust way to stop the rotation. Where the slot isn't very critical, left, right, because it's only taking away that 1 degree of freedom. I only need that top and bottom. So in my book, the mating surface and the hole and the width of the slot should be my datum features. And that would look something like this. A is the mounting surface, B is this hole, and C is the width of that slot. When I present this in class, time and time again, when I ask who should the datum features be, people will say, how about these outside edges? Well, as you look at this drawing, those outside edges are just there to hold the holes. They're not real critical. I have a general profile tolerance of 0.6 millimeters, and so I'm giving you a very generous tolerance all the way around here on those surfaces. If you start calling out these as datum features, then I'm going to have to tighten the position of this hole and the position of this hole in order to get something similar to what I'm getting out of this design. So the cost of the part is going to go up. If we look at our tolerance analysis for this, now what I've done here is to get the minimum height, minimum distance, I push the roller down against that surface. I push the stud down as far as it would go. I push the bracket down against the screw. And so if we start going through our vector analysis here, we find that in this bracket, we hand off from the screw to the bracket right here. So I would have a vector that goes to the datum plane of my bracket. Then I'd have a basic dimension, shown here is number 4, that gets me up to the center of the hole. And then I would have another vector that gets me to the handoff here, to where I hand off to the stud. So when I do my complete tolerance analysis on this, and we look over here at the results, the worst on worst, or WOW tolerance, right, the worst on worst ends up being 0.75 millimeters when you add up all your tolerances that go into this assembly. Now if I do what the shop wanted, oh, I'm sorry, here's another view of the vectors. I'll show you this first. So we handed off here to this hole, so I went down to the datum plane, then up to the center of that hole, and then down to this edge of the larger hole. But if I did what the shop wanted, they would want this surface and this surface to be my secondary and tertiary datum features. Given process capability, I'm going to have a bigger tolerance than going up here to this hole. So I've used a position of 0.6, kind of like remember we had a profile of 0.6 down here on this surface with the original drawing. And the same here, I have a position tolerance of 0.6 because of our process capability. You probably could hold this one a little tighter. This one's going to need more tolerance because you're going through a couple of bends, but let's just go with this for the moment. And now my vector loop looks something like this. Here's the handoff point. I go to the center of the hole, which is not the datum plane anymore. Then I have a vector that goes down to the datum plane. Then I have a vector from there up to the larger hole and then to the second handoff point. When I do my tolerance analysis and add up my tolerances, I end up with 1.125 millimeters of tolerance accumulation in this assembly. So it's 0.75 versus 1.125. So if the supplier says I'd like to use this and this is my datum features, B and C is shown over here, I'm going to say fine, but I'm going to have to greatly tighten this position tolerance and that tolerance to get the same result in my assembly. And usually when I say that, they'll back off. They'll say, no, I want those bigger tolerances. And so they'll go along with this functional approach. I just want to mention a little bit about creating alignment features. You know, when you're selecting your datum features, so many times I look at a part and I can't tell who's doing the alignment or constraining the degrees of freedom. If you take a design for assembly course, they're constantly preaching create alignment features when you're generating your geometry. It isn't always clear, though, how parts are aligned. And I'll just take you through this example. I believe I showed it in a previous brown bag. This part, sheet metal, is called a chimney. It goes into a cooktop. And the purpose of it is kind of backwards of what we think of with most chimneys. You have your burners here, and it's actually bringing combustion air down to the burner that's down here below the grates. In order to assemble this, they have to leave these screws loose and put the whole thing together to get these holes to line up, get the screws in there, and then go back and tighten everybody. And once it's assembled, it's very difficult to get to those screws. So that was their original design. We went through a design for assembly on this, and we created some alignment features. So we have these tabs now that we created. We put slots in here, and the way this now gets located is there's actually a little interference here. So it pulls the back surface of this new redesigned part up against the sheet metal, and you bring it up until you contact here and there. And we've also controlled the distance from this side of the slot to that side of the slot. Maybe I should not be so lazy and get my pen out here and mark these for you. So on the back surface we're mounting, you know, if you had your X-ray vision on, you could see that. And then we're hitting here and here. And then this distance from there to there is fairly tightly controlled. And so that's locating the part left-right. That became essentially our tertiary datum feature for those tabs. So here's the redesign, and we only need one screw to hold it in place now instead of the 4 they were using before. And there's no fiddling around. You just slide this into the slots, move it up, and turn that one screw, and you're done. So now we've created alignment features. Datum feature A is this irregular feature of size here between this little bump, and actually there's 2 of them, one here and one here, and the surface. B is these 2 surfaces down here, which are that spot and that spot right there. And then C is this width that I was talking about. So now I have a nice datum reference framework, and we can kind of see the datum planes here for our dimensional origin. So we had to create those alignment features because they weren't all that obvious. And about now you're getting kind of bored, so I thought I'd throw this in. Somebody sent this to me, and I just sat there and laughed for a while over it. So I'll let you see it one more time. Poor little dog. Okay. Well, let's go through an assembly now and apply this principle and see how it goes. This is a redraw of an actual fuel valve used in an automotive application. We have this block that mounts on the engine. Then this body that screws into the block. And then, let's see, the bobbin, and this bobbin would have windings around it. And this is an iron core that is molded inside the bobbin. So when you energize the windings here, this becomes a very powerful magnet. And it draws this piston to the right, so this valve opens. And when you take away the electricity from that coil, the spring closes it. So it's normally closed fuel valve. But when it's open, the fuel can come in here and it can flow out there. I'll show you another view of it. There we go. Let's look at a little bit better view here. And this is showing you the tolerance analysis that we went through. Our main concern is I don't want this to open too much, because if it does, when it slams shut, it'll shorten the life of this part that has a rubber plunger on the end of it. And if it doesn't open enough, I won't get enough fuel flow. So testing has determined that I'd like that gap to be 0.8 plus or minus 0.2. Now what that means is I have to take this 0.2 millimeters, and that's my budget. I have to budget that out to all of the vectors here so that I don't get a tolerance accumulation of more than that 0.2. If I have more vectors, each one of them is going to get less tolerance. Before we get into walking through that, I would like to mention, because some people are probably saying well, we deal with castings and we like processing datums. You know, when I think about a casting, and here's the casting for that block, it's really a separate part. Its function is to machine clean. And so when I look at a casting, I ask the question, what features in the manufacturing process are going to constrain the degrees of freedom to make sure that this thing will machine clean? In this case, we added 3 notches to that casting so that we can grab this on a 3-jaw chuck. The part will go in there and it'll mount up against these surfaces, and then we'll close in on the diameter with the jaws, and we'll use one of them to drive the part in the 3-jaw chuck. So our primary datum feature is these 3 surfaces that the tops of the jaws will touch on. So these 3 that we see here. And we made that datum feature Z. Then this diameter, it's made up of those 3 surfaces. We've made Y. And then we have these 3 widths here, but we're going to have the tooth that goes into this one a nice fit to drive it, and that's going to be our datum feature X. So these are functional because they constrain the degrees of freedom in the machining process. The standard tells us that features of in-process parts such as castings, forgings, machinings, or fabrications may be used as temporary datum features to create permanent datum features. The second bullet on this troubles me. It says such temporary datum features may or may not be subsequently removed. I strongly recommend that you create features that don't ever have to be removed. Sometimes there's no way around this, but you want to keep that track record if you can. And you also want to bring that over to your other part, to your machine part, your machine drawing. So now let's take a look at this block. It mounts on the engine on this surface, and it pilots on that diameter. And then this part actually pilots in here and mounts up against this surface. So when we look at this machine part, I'd want this surface to be my primary datum feature, and then this diameter to be secondary. But I might want an auxiliary datum feature up here. So when we look at the actual drawing, first let me point out that we've brought those cast datum features over to the machining print. So it's all tied together, it's all connected. Then I have located this feature, this primary datum feature, from my cast datum features, and I've tightened up the form of it. I don't want it rocking around, or it may be a sealing surface. Then I located datum feature B, this pilot, on that casting, positioned to ZYX, and then I've tightened up its perpendicularity to A. And then you'll notice over here, oh, let's see, where's C? C for rotation. We've used the width up here in this case. Could have used X. Could have gone with that also. Not so critical. Could have gone either way. But then I've added this datum feature D, which is where the other part comes in. So this surface is constraining 3 degrees of freedom on the mating part. And I wanted to be able to control where this surface is quite tightly to this surface because of that gap we're trying to maintain. I wanted to have a direct relationship there. So I did make this datum feature D so I could put the profile and parallelism on this surface back to D. Now if we look at this part, it's going to pilot on this diameter, and it's going to mount up against this surface right here. So when we look at the completed drawing, when you tighten up the threads, there's enough clearance, and it's a coarse thread, that when you tighten it up, you do make full contact here on that surface, and it does allow you to center up. There's a real nice fit here between here and the casting. So that becomes my datum feature B, and that's all I needed for this part. When we look at the bobbin is coming up against this surface, and this diameter and that diameter are locating it. So the question to ask there is, who's going to win in the assembly? Well, when you look at the fit that I have on this diameter and this diameter, they're a pretty nice fit to this part, to the brown part here. And so I'll probably only make contact with one high point on this surface. So I called one of these features A, the other one B, and made A-B my primary datum feature for the bobbin. So this was B, this was A, and then I said A-B, and then this became datum feature C. And then lastly, if we look at this is a subassembly that's purchased, and it is guided or located using this diameter, and it butts up against this surface right here. So we made this diameter A and made this surface B. So following this, what features take away the most degrees of freedom in the assembly? And by doing this, we kept the vector diagram, or the number of vectors, to a minimum. You don't always want to follow this approach. This is the starting point, okay? Sometimes you can allow a lot of variation in the assembly, and so it doesn't matter a whole lot, and you can give production what they want. It's not going to hurt you. There may be some other good reasons to select some different features. I know one I've run into a couple of times is where you have a highly polished bearing surface, and you really don't want people touching it to inspect. And so you'll use something else to come in contact, but you control the tolerance between those two features quite tightly. This is a starting point. You know, this is where we begin, and as you have your discussions, your drawing previews before the stuff goes on the drawing, you know, you get with your team. You may adjust, you may back off a little, but this is just to give you a nice starting point. It only works best most of the time. I'm not going to say that it works all the time, but it does work best most of the time in my experience. And I wish I could have gotten that statement into the Y14.5 standard, but I was outvoted. So there's what I wanted to present in this brown bag on selecting datum features, and I'd certainly be interested in your questions, comments, feedback.
I have unmuted everybody, so if you have a question, go ahead and ask.
Did I just hear a what, honey, in the background? Any thoughts on what you saw in this presentation?
Hey, Don?
Yeah.
This is Rich with Joel's group.
Having a hard time hearing you. Can you speak up?
Yeah, this is Rich with Joel's group in California.
Yeah, hi, Rich.
We, sorry about all the feedback, but I've got a question with a lot of our parts. When we have pretty much just static parts. We don't have a lot of dynamic parts, so our datum reference frames are usually pretty simple. And I was just wondering, with our datum reference frame, I noticed on your examples, there are times where you had your secondary and tertiary datum features controlled back to the primary in sequence. But then I also noticed that on some of the auxiliary ones you didn't. They just stood alone, like the datum feature D. And I'm just wondering if you can kind of speak to when it's appropriate, when it's not appropriate to have controls from subsequent datum features.
Let me back up to that.
Sorry about that. I muted Don for a second. Are you there,
So
Don?
I guess I'm not following the question.
Wait a minute.
Oh, so I was muted. All right.
You were muted, so I don't think they heard anything.
Okay, I was pointing out that datum feature D is located with respect to A, so it's controlled. So I'm not following the question, I guess.
Oh, you know what, Don, I'm sorry. Now that I see that the datum feature D symbol is not off of that profile to A feature control frame. So to me, it looked like it was just standalone. So I guess basically my question is, do we always want to have subsequent datum features controlled back to the primary in sequence, or can you just allow manufacturing tolerances to dictate how features are controlled to each other?
Well, according to the 14.5 standard, everything has to be controlled. If it's not real critical, of course, you're going to put bigger tolerances on it, I hope. But not everything has to be connected. It's sort of like you walk into a park, you go through the gate, and you're walking down a path. And there's a lot of paths in the park, and they're all interconnected. You don't go by one path and say, oh, it'd be nice to get to that path if I could jump that far. You know, they're all connected, and it's the same with parts. The features on parts have to be connected.
Hey, Don, can you go back to that sheet metal part in the pulley assembly?
Sure. We're getting there. I guess I should have just broke out of the presentation. Didn't think it was that far back. You didn't mean this sheet metal part. You meant the bracket.
Right.
Okay. How far back would you like me to go?
Let's see. Right there. Oh, is this the one? Yeah, that's the one. So in this case, you have datum feature A being the face. Datum feature B is that hole, and it is not positioned to, or it is not, doesn't have anything tied into A. And I think what driving at is, hey, do we have to do that too?
Yeah, that's a real good question, and I could be beat up for this one. Technically, B should have a perpendicularity on it back to A. In parts like this, sheet metal, where, you know, when you punch a hole, first it rounds over, then you get a little bit of it, and then it kind of blows away, if you look at it in section. So only this portion right here is really hole B, feature B. I can't gather enough data on that to prove whether it is perpendicular or not. And so what happens is people will put perpendicularity on a feature like this, and then the supplier, when they're trying to get through their first article inspection, keeps getting rejected because they can't gather enough data to prove it's good. There's no way for it to be bad. So a little common sense kicks in here. You don't want it to go too far, but on something like this, I wouldn't probably put a perpendicularity on it. Technically, it should be there.
Okay, Don, so then holding on to that same frame, on the right-hand side drawing where they were picking the outside edges of the surface, datum feature B is now the lower part of that bracket, and there's no control back to datum feature A. Is that
Same
all?
thing. Yeah, it's so thin.
Oh, okay, because of the thinness of the part?
Yeah. Now, also, I'll point out that if you look over here on datum feature C, I have it perpendicular to A and B, and some people would say, well, you just said you're not worried about the perpendicularity to A, and that's true, Although now it's got some bend to it, so it does have some some depth here. But the main reason for A is that's how the part works, and it's a nice stable setup. If I took A away, it'd be like setting your credit card on edge to just set on B. It's not sufficient in size to permit its intended use. So B could serve as a secondary datum feature, but never as a primary, in my opinion.
Now, Don, another question here on going back to the datum feature B you have there. I guess the way Rich and I have kind of batted this back and forth over the years, really, and the way I've always looked at parts like this is that the datum feature, the 6.2 hole you have there, is a datum feature which is used to identify datum B. And datum B is always going to be absolutely perfectly perpendicular to A, the datum itself, right? And so I've always looked at it like on a feature like that, on something like this, I would never bother putting a perpendicularity or a position or any kind of a feature control frame on that feature, because I'm not worried about that feature. As long as they hit the size, I'm happy, because I know that the datum itself is going to be correct.
Let me go back here to the figure from 14.5. And it's a slow computer, can you tell? Okay, here we go. See, I wouldn't tend to agree with you. If you look at this one, A is this face, and B is this diameter. Now, if I don't have a perpendicularity on B, the longer this thing gets, the more serious a perpendicularity error could be, because that means, let me kind of illustrate it here. This might come in exaggerated, something like this. And remember, this is going into a mating part where this acts bigger now with respect to A. Its size, and I exaggerated, but its size is good. There's its size. But its virtual size might not be good enough to fit the mating part. And so it would end up, it might even start to go into the mating part, but then as you try to bolt down and make full contact on A, you're straining the part. So, like I said, on something like that sheet metal, I'd leave the perpendicularity off because you can't prove whether it's right or wrong anyway. But you get into a part like this, I'm going to put it on there. Did that make sense?
Yep, it does.
Okay. Good discussion, though. Excellent. Anyone else? Or
I have a question. I have a question from Chris for you. Don?
Okay.
Okay. His question is, can you please give me 2 great reasons why someone should not use a pitch diameter as a primary datum? What is a preferred choice if the thread is critical? Thank you.
I don't know that I want to give 2 great reasons to not use the pitch diameter. Functionally, it's correct. There are thread gauges out there that pick up the pitch. They're not cheap, but if this is a really critical application and you need that, a lot depends on how the thread is created. If you're using a tap, for instance, you drill a hole first, then you use the tap. That tap has a lot of cutters on it, and those cutters are kind of like a 900-pound gorilla. They're going to go where they want to go, and so I have seen a lot of eccentricity between the pitch diameter axis and the minimum diameter axis on a hole that's had a thread cut in it. So, functionally, there are times you want to use that axis of that pitch cylinder. Now, if you can design around it, I'm all for that too. There's other things you can do, but a lot of people use them, and there's the gauges out there to do it. So, sorry.
Does it get back to the inspection the difficulty to inspect when you use pitch diameters?
Well, if you have the right gauges, thread gauges, it's not all that difficult. Company here in my town was machining transmission housings for the Chevy S10 and the Blazer, and before they would put the engine block onto the coordinate measure machine, they were using what are known as true pos pins that you screw down into the tapped holes that pick up the pitch. And then the CMM was probing the true pos pins to determine the axis. And by the way, the tolerances were projected out of the hole because you're worried about where the screw actually ends up. And so when they were inspecting the true pos pin, they were inspecting the projected tolerance zone.
Chris said thank you.
Okay, okay. Not what he wanted to hear, though.
Wait a minute.
Did I answer the other question?
Wait. Is there much lost by losing the minor or major diameters instead?
Well, I remember being at a company that did some measurements on this. It was a 1/4-20 thread. Okay, so an inch 1/4-20 thread. They wanted to help out production, and so they put a tolerance on, called it out as minor diameter. In assembly, they couldn't get the screws to go in because there wasn't very much clearance in the clearance holes. So then they measured the pitch cylinders axis, and there was a 13,000th difference in some of them, up to a 13,000th difference, which was enough to cause interference, and they couldn't even start the screw. So there can be a significant difference. Once again, it depends on how the threads are created. You know, if you chase a thread on a lathe, it's probably going to be pretty centered. So, but some roll threads and you know, form threads and threads where you use a tap, they can be off.
Thank you.
Okay.
Hey, Dawn, I have, I'm sorry, this is Joel again, and I kept looking at this picture up here. Can you redraw what you did on the skewed feature that's used to define
Sure.
data?
Yeah, maybe, what if I come over here with a, oh, I'm drawing on the wrong screen, hold on. So it's out of perpendicular.
Right. Now,
So,
you've
and
got,
Joel, the size is good, right?
correct, size is good.
Okay.
Okay, now, if you go from the actual part and you go and look at all of the other features on there that are positioned to datums A and B, with A being primary, B cannot be on that skewed axis. Am I correct?
No, you're absolutely right. Let me change colors here. Yep, when I close in on B, I have to use a related actual main envelope, is the new term in the standard.
Right.
So I will get a datum axis that looks something like that.
Great. Okay.
And that's not the issue. The issue is the mating part.
Right. Exactly. So it really comes down to functionality.
The reason why you put the perpendicularity on here, sure, yeah. Yeah, I want it to go together.
Yep. Okay.
Great. Other questions or comments? Well, as with, while you're thinking of it, you know, as with all the brown bags, it's kind of a shot in the dark. I really appreciate when people give me suggestions for brown bags. And, you know, this one I threw together, I hope you got something out of it. I do appreciate feedback, so I know if I'm on the right track. So I hope you found it interesting. Anybody have any other questions or comments?
Don, if I could, since nobody else is speaking up, this is Rich with Joel's group. So my confusion is when I see that the feature control frames and the datum feature controls, I think where Joel and I have kind of bounced back and forth is he keeps going back to that, you know, the standard says that the datum feature planes are mutually perpendicular or normal to each other, why are we putting these controls? And could you speak to the difference between datum features and datum signatures?
Exactly. Yeah, that's where I was going. The standard doesn't say datum features are mutually perpendicular. In fact, there's many times they aren't. The datums themselves are. The whole theory behind datum reference frames is, if you go back to the 1966 standard, and I really like to have my datums in red, so I'm going to do that. You know, the standard tells us that we have these three mutually perpendicular planes. Where are these three mutually perpendicular planes? Well, they're in the processing equipment. And we expect that our processing equipment is better than the parts that we're dealing with. So I have these three mutually perpendicular planes. Now, we take crummy features on the part. Crummy features. They're not perfect. We call them datum features. And we use those features to take this part and align it to these beautiful planes. So here's your datum, and they are mutually perpendicular, and they're considered to be perfect. They're theoretically perfect. But we use crummy features on the part to line the part up to those planes as best we can. Is that what you were after?
Yeah, that's pretty much how I've been thinking of it. I think that at times Joel and I have gone back and forth thinking that the diameter that's 50 millimeters on the high side of 49.98, could you just not let that manufacturing deviation in size dictate where datum feature B is and not worry about it controlling back to datum feature A? And I've just always, from all of your training and seminars, I've always leaned towards, well, yeah, I want to control it, but it has caused confusion to myself, and I wonder if sometimes am I over tolerancing or over constraining a part on my drawings by doing that. You know,
yes. So many people have left that off because they're saying just what I'm hearing here, that, well, they're the datum features, they're perfect or nearly perfect. That happens so much that we added the words in the 2009 standard saying that you have to control these features because it's caused so many problems. In our fundamentals training, we have a redraw of a cutter tool insert that looks something like this. And I'll just show the side view here. So this is datum feature A, and this one is B, and this one is C. And there's nothing wrong with that. And we need controls on these. A has a flatness, B has a perpendicularity back to A, and C has an angularity to A and B. Okay, so I have controls on those. But then there's a hole out here, and we see this, and we see a dimension like this. And some people say, oh, look at that turkey. He's dimensioning from some theoretical point in space. And the fact is, I am not. I'll change colors here. Because what I've shown you so far are the datum features. The datums themselves will be simulated by a nice plate here. And we'll have a simulator here. And we'll have a simulator at the basic angle here. I'll exaggerate it a little bit. Okay, but I'll put it at the basic angle. And then I slide my part into this setup. Now, where are the datums? I haven't shown you them yet. Let me go to some other color. It'll show up, I hope. We'll try this. Certainly the first datum plane, you'd say, oh, okay, it's right there. It's coincident with that plate. And the second datum plane is coincident with B. So it's right along here. But where's the third one? Well, the rules are, now we're talking about the datum planes, it has to be at right angles to A, and it has to be at right angles to the one established by B. So where the simulator for C intersects down here, I get my third datum plane. And that's what I'm dimensioning from. If I build a fixture, I'd put a chunk of steel right here in that fixture so I could touch off it with a probe to come out to measure that hole, find out where that hole is, because my origin of measurement's back here. So I think this kind of shows the difference between datums, which are theoretical and perfect, right, mutually perpendicular, datum simulators, which are your setup, and then your datum features themselves, which are the crummy things on the part. I don't know if that helped.
That does. Thank you, Don.
Yeah, very much.
Okay,
We have to boot out of here. We can
Okay.
boot out.
Thanks
you.
a lot, Don.
Okay, hope to see you in another brown bag. Thanks for supporting the premium site. And keep those cards and letters coming with suggestions, folks.
Thank you.
Any other questions from anybody, Wendy?
Chris says, good discussion. Have a great Christmas. Thank you. You too, Chris.
Oh, Merry Christmas. Happy Hanukkah.
And Tungden says, happy holidays and excellent topic. Thank you very much.
Great.
Happy holidays to you too. Okay, I guess that's it. So thanks, everybody, and we'll see you at the next brown bag.
Thank you much. Happy holidays, Christmas, Hanukkah, and all that. Festivus? No. Take care, everyone.